Good morning, class. Yesterday we collected data. No, we didn't. You were given data. Sorry about that. Um, so that we could calculate something called the rebound ratio of one of these. And this is the one that I used for the data I gave you yesterday. And basically what happened was I took this to a certain height, released it, it bounced, and then I measured the height that it came back to, right? So I had the initial drop height, and then I had the rebound height. What was kind of surprising about that to me, anyways, was that this ended up being a linear relationship. In fact, if you look at it, right, this was the scatter plot a student did. This is from yesterday's work. And you can see that the a line was a nice fit. In general, I didn't have points. I didn't have a residual plot that indicated a curve should have been used. This was a linear relationship. The relationship that the student found was this line of best fit was y equals 0.6 x plus 2.4. The y-intercept is a little bit problematic if we think about it, because remember, if we had a initial drop height of 0, it's not going to rebound to 2.4 inches. It's not my experience that when I set one of these on the counter, they just automatically jump up 2.4 inches. But I understand why we have that. It was something about the way the data was. So this is a great response for A. It says the rebound ratio for my team's ball is 0.6. The rebound ratio is reflected in my line of best fit because it's the slope of the line of best fit, also known as the rise over the run. The rebound ratio is reflected as m in my y equals mx plus b equation. The rebound ratio is shown in my table because it's the number that determines what the rebound ratio from the ball, from the drop, rebound ratio from the drop point of the ball. So what's nice is because this is linear, it seems like I can have a certain height, drop it, and it's going to rebound up to a certain place. In fact, it looks like this particular one recovers about 60% of its initial drop height. So if I drop it from an initial drop height of 100, this model is predicting that from 100, it should rebound back up to 60, right? If I dropped it from 40 times 0.6 should be a 28-ish. So the model is saying right there about 28. So what's nice about this is I can think about, okay, what if instead of just dropping this once, what if we dropped it and we observed its height each time, right? After several bounces, let's say instead of just one bounce, we let it bounce 3, 4, 5 times. What would that data look like if we were to graph the number of drops or number of bounces, and then the height of the ball, number of bounces versus height of the ball? Well, that's what we're going to do today, so let's get started with that. So today we are in section 5.1.3, and the title for today's lesson is Go. What is the pattern, the bouncing ball and exponential decay? Yesterday you found the relationship between the height from which a ball is dropped and its rebound height, and we found that maintains a constant ratio. It was about 0.6 for each of the heights. In this lesson, you will continue this investigation by exploring the mathematical relationship between how many times the ball has bounced and the height of each bounce. So we're going to look at multiple bounces. So you start at this height, and then it has the rebound height, and then again, and again, and again. Consider the work you did in lesson 5.1.2, in which you found the rebound ratio for a ball. What was the rebound ratio for the ball your team used? Well, our team is Team Shasta High this year, and the ball that we had a rebound ratio of 0.6. So even if you had a different one, we'll just go with 0.6 today. Did the height you dropped the ball from affect this ratio? Apparently not. Which was kind of interesting. I'm sure there are things that would affect it. I would expect that if I dropped it from maybe a height of 2 miles up in that's not space, it's at the edge. I don't know where the atmosphere ends. Or 3 football fields, like high, maybe it would drop. I mean, it would change, maybe because of wind resistance or something. But in this very small room size, classroom size experiment, it seemed like it kept coming back to say it recovered like 60% of its initial height each time. So I would say no. If you were to use the same ball again and drop it from any height, could you predict its rebound height? Explain how you would do this. Well, I just was talking about that. If I dropped it from a height of 100 inches, it would come back 100 inches. Something that's kind of interesting, and we can see this in the graph from this student's work, is we did have the initial drop height was measured in inches, and the rebound height was measured in inches. Well, the slope is this rise divided by this run. So if I take some inches divided by inches, I end up getting a unitless measurement, right? So the rebound ratio doesn't depend on the units used. So I could easily say, oh, let's say that they were feet, right? Because I'm going to recover in feet. So if I drop it from 50 feet, 50 times 0.6 should come back to about 30 feet. So there's that. So it seems like what we do is we just take the height that we drop it from and we multiply it by the rebound ratio. Okay, so this is the first question I want you to do, and you are going to ask to come up with a table and some predictions. And I would like to see, it says we're going to graph it, and then it says should the line be discrete or continuous. So imagine that you drop the ball that you used in problem 5-19. So the one that we used was the blue one with the swirl on it, and it had a rebound ratio of about 0.6. But this time you let it bounce repeatedly. So if I was to think about a table of values, right, at bounce 0, I'm at 200, right, because it hasn't bounced yet. At the end of one bounce, it's going to come back a certain amount, right? And I think you guys can talk about that and figure that out amongst yourselves. What's the height that's going to return to? And then that height that it returns to is now your new initial height, right? And then it's going to bounce again. What's going to be the height after that first bounce, after the second bounce, after the third bounce? So predict your ball's rebound height after each of 6 successive bounces if its starting height is 200 centimeters. Create a table with these predicted heights, and then discuss and decide which ones are the independent and dependent variables in this situation. I think I'm going to impose, well, I mean, if we think about it, right, the height of the ball is, right, really depends on how many times it bounces, right? So I would say the number of bounces is independent, and the height the ball is going to be depends on the number of times it has bounced. So I'm just going to say our independent variable will be number of bounces, and dependent variable would be the height of the ball after that bounce. Graph your predicted rebound heights. I highly recommend that you use Desmos for that. It's a great tool, and your graphs look fabulous when you do that. If you are going to go with that Desmos route, go ahead and answer these questions in the same Google Doc, so you don't need to use multiple. You don't need to upload handwritten work and this. Just go ahead and type your responses and include the graph there. And then, should your graph be discrete or continuous, how can you tell? Well, we've been talking about this a little bit, and you've seen it kind of coming up over the last couple days, but if you think about what our x-axis is, it's number of bounces. So what does it mean for a ball to bounce 1.2 times? Right? Does that make sense? I don't think so. I think we're counting number of bounces, so it's 1 bounce, 2 bounce, 3 bounce, 4 bounce. So I would say that this is discrete because our x-axis is just keeping track of a number. How many times did the ball bounce? We are skipping question 5-30 this year, although this is great fun to test. Yes, we are not going to be doing that because I don't know that you have these materials at home. But we are going to go on to 531. So a function can be used to model the data from 5-29. A function can be used to model that data. And we've been doing that for a while, right? We've been using linear functions to model data quite often. It says compare your graph for the height of successive bounces from 529 to the graph of drop height versus bounce height that we collected yesterday. So you can look at the one we collected yesterday, right here, and you can make a comparison between this graph and the one that you've produced today. Can you use the same kind of equation to model the two situations? That is, what family of functions do you think would make the best fit for each data set? Discuss this with your team, and you can spin up a chat and discuss that, or share a doc and discuss that with your classmates. So respond to A. So I'm looking for a response from 31A. And then finally, describe how the pattern of growth for successive bounces is the same as or different from other models you've looked at previously. So when I go down the line and I look at successive bounces, what am I doing to go to the next one on the list, to the next one on the list? Right? What does that operation look like? And then how is it different from things we've done in the past? And then finally, read and consider and give me a response for question 32. It says, if you continue to let your ball bounce uninterrupted, how high would the ball bounce after the 12th bounce? Would the ball ever stop bouncing? Explain your answer in terms of both the experimental data and your equation. So let's not focus so much on the physical model and what it would be, because that'd be awfully hard to record. But what would it mean in terms of the model that we have and the data that we collected? Okay, so to summarize what you're responsible for, we've discussed 28 together, and it's important information. You need to know that moving forward. I'm looking for a response from 29. 29 should include a graph. Of course, when you give me a graph, it should be labeled correctly. Desmos does a great job of doing that. You are going to be spelling out in your doc which one's independent, which one's dependent. Should it be discrete? Should it be continuous? And I should see a data table in there with 6 successive bounces. So of course the 0th one is not a bounce, so you're going to have 0 at 200 and then 6 bounces below that. You are not doing question 30, but you are responding to 31 and 32. Thank you very much. I look forward to seeing you in class and online. This is Mr. Roberts. Goodbye.